Let me ask you something. What if you could take a massive 20 gigabyte AI container, the kind that takes forever to start, and get it up and running in just 2 seconds? Yeah, 2 seconds. Sounds pretty much impossible, right? Well, today we're going to break down exactly how it's not just possible, but how it's being done.
And look, we're not talking about some small 10% improvement here. We are talking about a performance boost of over 360 times. That is a mind-bending leap in performance, the kind of thing that completely changes how you architect your systems. So keep that number, 360x, in your head as we dive in.
So the big question is, how on earth do you go from a 10-minute coffee break while your container starts to a 2-second blink of an eye? Well, to really get the genius of the solution, we first have to understand the problem. And it's a huge, expensive problem that pretty much anyone working in AI today knows all too well.
And that brings us to what I like to call AI's big startup problem. It's this massive, kind of invisible bottleneck that's just quietly burning through cache and slowing everybody down.
Okay, so the root of the whole issue, it's simple: size. AI container images they're enormous. We're talking 20 gigabytes, sometimes way more. They're stuffed with these giant model weights, heavy-duty dependencies like CUDA, PyTorch, the whole shebang. These are not your tiny little microservices, not by a long shot.
And that huge size has a very direct, very painful consequence: incredibly long cold start times. So you're stuck, right? When a new request comes in, you either make your user wait minutes for a new container to spin up, or you pay a fortune to keep a bunch of expensive GPUs just sitting there, running idle in a warm pool, just in case. Neither of those is a great option.
So why is it so agonizingly slow? Let's actually look at the standard workflow, the step-by-step process that basically every container runtime out there, like Containerd in Kubernetes, follows by default. It's a very linear process that really hasn't changed in years.
This whole process really breaks down into 3 separate bottlenecks that happen one after the other. First, you have to download the entire multi-gigabyte image. That's your network getting slammed. Then you have to decompress every single layer, which is often single-threaded and just hammers your CPU. And finally, you have to write all those uncompressed files to disk and mount them, which, you guessed it, is an I/O bottleneck. It's just this one long, slow, sequential slog.
And the result of all those bottlenecks stacked on top of each other? For a typical 20 gigabyte image, you are easily looking at a startup time of over 10 minutes. In the world of autoscaling and on-demand computing, that's an eternity. It's just not practical.
And this right here, this is the fundamental flaw, the absolutely insane inefficiency at the heart of the whole problem. The system forces you to download, decompress, and write 20 gigabytes of data, when in reality, your application might only need, say, a few hundred megabytes to actually initialize and be ready to serve that first request.
So this is where it all gets really, really cool. If the whole problem is waiting for data you don't even need yet, the solution is obvious, right? Only get the data you do need exactly when you need it. Let's see how this completely new model works.
And the core concept that makes this all possible is called lazy loading. It's a simple but incredibly powerful idea. Instead of preloading everything, the system fetches data on demand. When your application tries to read a file, and only then, is that specific piece of data actually retrieved.
This is a complete paradigm shift. It's a totally different way of thinking. We're moving away from this slow, wasteful, download everything first model to a super efficient, lightning-fast, access files on demand model. But to actually pull this off with container images, well, that requires solving some really tricky technical challenges.
Okay, so how do they pull off this magic trick? It really happens in 2 parts. And the first part is a clever bit of engineering that you do at build time, long before your container ever gets scheduled to run. You have to fundamentally change how the image itself is structured.
Here's the big roadblock. A standard container image layer is basically just a big compressed file, a tar.gz. It's a stream. And if you want to access a single, tiny file that's buried deep in the middle of that stream, you have no choice but to decompress the entire thing up to that point. It's impossible to just jump straight to the data you need.
So here's the solution from Tensorfuse. At build time, it converts that standard image into a new, seekable format. It cleverly separates the metadata, the list of files, their locations, permissions, from the actual file data. This metadata becomes a super compact table of contents for the entire image, giving you a map of exactly where every single piece of data lives.
All right, so with that new, much smarter, seekable image format sitting in our registry, we're ready for part 2 of the magic.
What happens at runtime when Kubernetes actually says, okay, let's start this container?
Okay, so walk through this with me. The app inside the container tries to read a file. Let's say it doesn't import Torch. The Linux kernel intercepts that request and passes it to the Tensorfuse daemon. The daemon just glances at its table of contents, sees exactly which bytes it needs, and then, this is the coolest part, it makes a tiny HTTP range request to the registry to grab only that specific chunk of data. It gets decompressed instantly in memory and then handed right back to the app. And the application? It has absolutely no idea the file wasn't sitting there on disk the whole time. It's completely transparent.
This quote from the source material just sums it up perfectly. Your container registry, which you probably thought of as just a slow place to store tarballs, is totally transformed. It becomes a high-performance network drive that your container can read from instantly, piece by piece, completely on demand.
Okay, so we've gone through the theory. We've seen the clever engineering that happens at both build time and runtime. Now let's get to the good part. What does this actually mean in the real world? Let's look at the numbers.
And the hard data here really speaks for itself. With the standard method, it takes over 12 minutes just to unpack the image and get to the container's starting command, its entry point. With this new approach, 2 seconds. That's a greater than 360x improvement. It's just wild. And even for the VLLM server to be fully ready to serve requests, we're going from 12.5 minutes down to just 20 seconds.
I mean, this chart just makes the difference brutally clear. It almost looks like a mistake. On the left, you've got the standard startup time way up there at about 725 seconds. And on the right, you can barely even see the bar at 2 seconds. It's not just an improvement, it's a total game changer. You've effectively eliminated the startup time.
So, what's the big takeaway here? Well, for starters, you completely eliminate that download and unpacked bottleneck. It's just gone. That means cold starts are basically a thing of the past, and that has huge business implications. You can stop paying for all those expensive idle GPUs, which saves a ton of money, and your workloads can scale up and down almost instantly to meet demand. It's just a way more efficient, more elastic system.
And that really leaves us with one final big thought. When a fundamental constraint like container startup time is basically removed from the equation, it opens up entirely new architectural possibilities. So I'll leave you with this question. If your 20 gigabyte container could start in 2 seconds, what would you build next?